being here. And today my talk is on the design of alkaline superionic conductors with machine learning. So as you can see, I have highlighted two aspects of the talk that are critically important. One is basically that this talk is on alkaline superionic conducttors. But more importantly, I'm specifically focusing on how do you actually go about using machine learning to accelerate the design of alkaline superionic conductors. Now, I've given a lot of talks in the machine learning session on, and I have to educate them on batteries. So here I'm really trying to do the reverse. I'm going to really talk about machine learning to a battery audience. Okay. So this was work that was funded over the years by ONR, then followed by Shell and Nissan, and the computing resources is from Exceed. So I don't need to talk about why we are looking at solid-state batteries, but I just want to remind everyone what are the kind of things we look for in the solid electrolyte of our solid-state battery, right? So obviously, being an ion conductor, we want that solid electrolyte to have as fast an ion conductivity as possible given other limitations, right? So typically in the literature, we talk about ionic conductivities that needs to be at least 0.1 millisiemens per centimeter. And ideally, we want it to be at least an order of magnitude or two higher than that. Now, perhaps more importantly at this juncture, we are also very interested in the interfacial stability of this solid electrolyte with either the cathode or the anode, right? And that actually, I would say, is probably the limiting factor for all solid-state batteries today. So I'm going to talk about how machine learning can actually be used to address both of these key design requirements for alkaline superionic conductors. So what is machine learning? Machine learning is basically the scientific study of algorithms that use a computer to perform a task without explicit instructions, but rather using patterns and inference, right? So as many of you may well know, machine learning is, of course, a very hot topic today. When we talk about self-driving cars or playing the game of Go or predicting the weather, all these things rely on machine learning, right? So machine learning is really the intersection of three things, which is basically data, science, and algorithms. And I would like to think that my group actually operates in the intersection of this, where we really try to combine data together with algorithms to try to address some of the quality issues in material science. We try to develop new algorithms that are specially customized for the material science domain, and we also use them in applications like screening, right? Now, so you have heard from Gert, and you have heard that in almost all his works, the way that you go about predicting ionic conductivity, at least for non-dilute diffusion, is primarily done using ab initio molecular dynamics, right? Now, ab initio molecular dynamics is basically combining the equations of quantum mechanics to calculate things like the forces, and you combine them with Newton's laws of motion, and then you just let the atoms move around, right? So once you actually let the atoms move around, you basically can apply the equations of kinetics and try to derive out things like the diffusivity. Okay, so this was work that was done by Yifei Mo and myself back in 2012 when the LGPS material was first discovered by Professor Kano. Right, so this was actually our very first foray into ab initio molecular dynamics as a technique. Now, it has grown increasingly clear to me over the years, 10 years, right, that there are severe limitations of AIMD. And Gert actually has alluded to some of them, right? So your simulation cells are small. So when we did LGPS, we basically just use a single unit cell. The simulation temperatures tend to be high. Usually people start simulating at 600 K, if not higher. And as you well know, most of the alkaline superionic conductors, they basically are not stable at above, say, even 400 K, right? So in essence, we are simulating something at a very high temperature, and then we are extrapolating it down to room temperature and assuming that that extrapolation is actually correct. And I'm going to show you that that's actually not the case, right? And of course, being that we are doing AIMD, then of course it depends on the accuracy of the DFT functional that you use. And by default, we choose the cheapest functional that we can get away with, which is PBE, right? And we all know that PBE has a lot of errors in the prediction of certain properties, right? So nevertheless, AIMD, of course, has led to practical materials design. This was a follow-on work from the LGPS work, where we basically tried substituting different cations into LGPS and trying to figure out whether we can actually get a cheaper superionic conductor by changing the germanium for something like silicon and tin. And in fact, we found that we can, and this work was actually subsequently verified, right? So, however, AIMD has been known to fail spectacularly, right? So this is, I'm showing you two examples from work that my group has done over the years, as well as a group from, another work from Yifei Mo's group on two very different superionic conductors, right? So the first one is this LS7P3S11 material. What you see in green here is basically what we simulated using AIMD, and we extrapolated down to room temperature, and we found a room temperature ionic conductivity of 57 millisiemens per centimeter, right? And the experimentalists in this room will basically immediately tell me, well, we have never measured any LS7P3S11 with 57 millisiemens per centimeter. Everyone has measured it somewhere between 4 to 17 millisiemens per centimeter, right? Now, similarly for this Li3YCl6, it is known that the original report on this particular halide superionic conductor has a conductivity of 0.72 millisiemens per centimeter at room temperature, and this work from Yifei Mo's group actually found used AIMD to calculate it at 40 millisiemens per centimeter, right? So again, a huge overestimate, right? There is some discrepancy that is happening between the AIMD predictions and the experimental predictions, and we have not figured out why that's the case, right? And I'm going to say that it's mostly down to the way that we are simulating these materials and the fact that we are using high temperatures and small cells, okay? So this is where machine learning comes in, right? So the way to get away from this AIMD limitation is really by replacing this quantum mechanics part with some parameterization of the potential energy surface, right? So in essence, you want something that tells you what's the energy and forces on the atoms as a function of the atomic positions. And instead of doing quantum mechanics, we use this, and then what we get is a simulation that is orders of magnitude faster. It scales linearly with number of atoms, and we can run simulations on 1,000 atoms, million atom systems for nanosecond time scales rather than just a few hundred picoseconds, okay? So this is where machine learning actually comes in, right? So what we do is that people over the years have developed what are called machine learning interatomic potentials, where you basically describe the local environment around the atoms as some descriptor. So for example, the distances and angles between them, or using something like the neighbor density. And you then use machine learning to basically try to parameterize what's the energy and forces on each atom with respect to this local environment descriptor, right? So I'm not going to go into the details of the machine learning algorithms. It can be either simple linear regression. It can be also things like more sophisticated things like neural networks, right? And once you are able to do that, you will find that machine learning interatomic potential development is actually very systematic and automatable, and they are much, much better than traditional interatomic potentials in terms of accuracy, right? So my group has actually developed a standardized workflow to actually create interatomic potentials for any chemical system that we are interested in, and we can do this easily within a few weeks or at most a month. And we have actually done interatomic potentials for a large number of systems, and we have benchmarked them, and we found that all the different machine learning interatomic potentials actually perform much better than your traditional embedded atom or mean potentials in terms of accuracy, right? So this is basically energies and these forces, and the darker the color, the lower the mean absolute error in the energy or forces. And you can see that all these machine learning interatomic potentials are all significantly better than your EAM and MEM for a wide variety of systems, right? So recently, we have started to apply this to the lithium superionic conductor problem, right? We have found that basically AIMD doesn't seem to be giving us particularly good predictions. So why not develop machine learning interatomic potentials for lithium superionic conductors? And instead of doing it for just one system, we decided to challenge ourselves and do it for 3 different superionic conductors with very, very different anion chemistries, right? So Al3YCl6, Al7P3S11, which we know the AIMD is wrong, and also this LLTO oxide superionic conductor. And what we found was that basically when we apply the trained machine learning interatomic potentials to nanosecond level MPT, MD simulations, we are able to actually simulate a wide variety of temperatures from 300K all the way to 800K. And what we found was that unlike that nice linear extrapolation that you see in practically all the AIMD papers out there, it's actually not clear that it is just a linear Arrhenius regime, right? We found that all 3 lithium superionic conductors to varying degrees have this kink in the Arrhenius plot. There's a high temperature regime, which is where you actually do your AIMD on, and then there's this low temperature regime, which actually has a significantly different activation barrier for diffusion, right? Now, because of this kink, extrapolating from the high temperature will just lead to a significant overestimate of your ionic conductivity, right? And what we found was that when we simulate all the way down to room temperature, we actually get ionic conductivities that are much, much closer to the experimental values. In fact, they fall right smack in the middle of the range of where the experimentalists have measured them, right? So in other words, what I'm trying to say is that it is no longer sufficient to just do AIMD and then draw a line and then just say, okay, my work is done, I believe my results are accurate, and this is going to be the conductivity that I get when I actually synthesize my superionic conductor, right? And again, this is something that is somewhat not new, okay? Experimentalists have been measuring these kind of kinks in Arrhenius plot all the time. So this is actually the LLTO material. This was work done by Salkers back in 2011 in solid-state ionics. And you see that you actually see exactly the same kink behavior between the high temperature regime and the low temperature regime, right? And we actually found that this kink actually consistently happens at around 400 to 525 Kelvin, right? Now, because we are doing computations, we can actually look at the origins of this non-Arrhenius transition. We basically plot the lithium trajectories above and below the transition temperature. And what we found was that in almost all the cases, there's an activation of new diffusion pathways, right? So at the high temperature regime, you actually have diffusion pathways that were not available at the lower temperature regime. And that is why the high temperature regime actually has a lower activation barrier overall. And in some cases, that actually changes the dimensionality of your diffusion, right? So for example, Al3YCl6 at 300K is basically a quasi 1D conductor. There's a fast diffusion channel in one layer, and there is no diffusion across the layers. But once you actually bring it up above the transition temperature, you actually get full 3D diffusion. And this is also the case in the LTO material. In the L7P3S11, then that is actually already a 3D conductor, so you don't actually get a change in dimension diffusion, the dimension of diffusion, right? Now, this also suggests that there are ways in which we can potentially improve lithium superionic conductors, right? Instead of just living with the low temperature regime, if we can somehow try to stabilize the high temperature regime and allow it to continue to activate those diffusion pathways at lower temperatures, we can potentially significantly increase the ionic conductivity in these systems, right? So just to show you an aspect where we actually use this in a practical materials design. So this is a related material. This is the Na3YCl6 material, and this is work that was done in collaboration with Shirley Meng. And what we decided to do was to try to, by the way, the NYC material, unlike the LYC material, is actually a terrible superionic conductor, okay? So the conductivity of this is so low that it is impractical as a solid electrolyte. What we found was that using computations is that if you dope zirconium in it, other than just creating that additional sodium vacancies, you significantly actually improve the conductivity in this material. Again, you will notice that we fitted a machine learning interatomic potential to this system, and we found that, again, there's this kink behavior in the different Arrhenius regime, and our predicted ionic conductivity is, again, very, very close to what experimentally was measured by Shirley's group, right? If we compare the lithium trajectories in NYC and the NYZC material where we dope the zirconium, we can actually get some insights into what exactly is happening with the zirconium dope material other than just sodium deficiency, right? We found that essentially we have much greater degree of polyhedral rotations, and we can actually artificially freeze the polyhedrals, and we found that basically if you freeze the octahedrals, your conductivity is exactly the same as the NYC material, while if you actually allow it to move, there's actually a greater degree of octahedral rotations, and there's a corresponding increase in the ionic conductivity. So now, this is where I think Professor Naza has actually talked about this before. I think this is somewhat related to that paddle wheel effect. I know Gert doesn't believe in it, but I do think that this actually provides a little bit of evidence that that octahedral rotation is not doing.
It's wrong, right? Every time you freeze a degree of freedom, the conductivity decreases.
No, we actually freeze the NYC as well. So if we freeze the NYC, we get basically exactly the same conductivity. But if we freeze something with dope, the dope NYC material, we find that the conductivity is actually exactly the same as the NYC.
You freeze the rotation, not the polyanion. But if you freeze the rotation, rotate and it moves, that would be approved.
Yep, maybe you can do that. Yeah, but I'm just saying that compared to NYC to the dope NYC, basically if you freeze it, it's basically the same as the NYC. And in the NYC, freezing has no effect, basically. You will still get the same conductivity with and without freezing. But in the dope NYC, you actually do see a significant decrease in the conductivity. All right. This is actually a pretty good conductor. It's not a great conductor, so we can't use it as a replacement solid electrolyte. But the nice thing about this is that it is stable to cathode voltages, and we use it as a cathode composite material. And we found that it can enable the cycling of this full all solid state batteries to quite a high number of cycles. And this work is actually already published, but recently we actually have been looking further into this NYZC space, and we find that there's actually a lot of untapped potential there. We found that actually by disordering the yttrium and zirconium, as well as amorphizing this material, potentially this material can go beyond 1 millisiemens per centimeter, right? So these results are not yet published. I'm hoping that my collaborators, Raphael Kerman and Shirley Meng, is going to try to verify some of these predictions, okay? All right, in my remaining time, I'm going to skip past this one, and I'm going to talk about, I will continue. So the other aspect of all solid state batteries is that we want to understand the interface, right? And most of the time we have been working with either simple thermodynamic estimates of the reactivity between the materials, or we have been trying to simulate this using AIMD, right? Now, the problem with interfaces, of course, they are inherently low symmetry. And also because they actually have a greater number of species, because you are interfacing two materials, it's actually a difficult challenge for your traditional interatomic potentials, right? So this is again where machine learning interatomic potentials come in, and here we actually use a more sophisticated technique based on active learning, where you, instead of just building the interatomic potentials straight off, we basically first build an initial potential, and then we iterate on the potential using what is called an extrapolation grid, and such that we actually train a potential that can actually model the interface accurately, right? So we use things like the interfacial energies to basically converge the potential. And here we are looking at a simplified system, which is the sulfur Li3PS4 cathode solid electrolyte interface. I know a lot of people working in lithium sulfur batteries are extremely interested in this. And we show that essentially with a minimum number of iterations, we can actually get a potential that can model this interface pretty well, right? So with this, we can now do realistic interfacial modeling, right? So we can actually construct 8,000 atom, this by no means the limit, systems of things like the sulfur Li3PS4 interface. We can run simulation times of up to nanoseconds, and we can monitor the formation of things like the lithium polysulfides in the computational experiments, and essentially look at how the coordination changes, and looking at whether any of these sulfides actually would have any mobility, these polysulfides would have any mobility, right? Now, one thing that is missing from this is, of course, this is a potential that actually doesn't explicitly include reactivity, so there's no electron transfer per se. There are newer potential forms that can include electron transfer, but this does include it in an implicit manner in terms of the local environment changes and the effect of that has on the energies and forces of the system. Okay. All right. Finally, I'm going to talk about this new development in my group, which I think would have the potential that can significantly expand our search space for lithium superionically conductors. Okay, so all the machine learning interatomic potentials that you have seen so far, they are all specifically trained to that chemical system that we are interested in. So I'm interested in Li3PS4, I train the Li3PS4 potential, right? Now, instead of doing that, why not train a potential that can work across the entire periodic table like DFT does, right? And to do this, we have to adopt a different way of constructing the machine learning interatomic potential. We instead use a graph-based representation of the material. Okay, so the atoms are basically the nodes in the graph, and the edges in the graph are basically your bonds. And instead of just using a graph-based representation, we also include a many-body term that is taken from the Tishov potential, right? Now, to train this potential, we actually utilize one of the most underutilized data in the materials project today, right? Everyone goes to the materials project and they search for structure, they search for energy, they search for the band structure, right? What they didn't realize is that since the materials project has been around for 10 years, we have done about 100,000 structural relaxations. We have easily more than 100,000 energies. We have close to more than 10 million forces and 1 million stresses, right? So this is, by definition, the big data set that everyone is looking for, right? And they are all, we can just throw all this data into this graph-based representation of materials and build a machine learning model that can essentially predict the energy and forces based on just the coordinates of the atoms alone, right? Now, we can actually show that this potential actually greatly expands the universe of materials that we can explore. So we actually show that you can use this potential for doing actual structural relaxations, okay? And the eventual energy difference between the ground state and the calculated energy, we actually can get it very, very close to what DFT would predict. We can even use it for something like an AIMD simulation, or rather MD simulation. And this is just one example. So this is the LYC material, and we show that we can actually run an MD simulation using this universal potential, and we can actually get a prediction that is reasonably close to experiments, right? To the AIMD result, right? Now, what this means is that we can now do a massive scale search for new lithium superionically conductors, right? And I would say this is more of a brute force approach. We basically just went ahead and substitute lots and lots of materials with lithium and other non-redox active elements, and we basically ran a huge scale search for using this as an MD simulator to basically look for new lithium superionically conductors. What we are encouraged by, at least, is that there is definitely a correlation. We do find that all our known lithium superionically conductors all fall somewhere close to where we expect them to be. So this is a plot of basically the mean square displacement at 1200K versus the mean square displacement at 800K. And if you have high diffusivity, we will expect that the mean square displacements will be high, right? And all your favorite materials are all here. LGPS, LZPS is also here. And all the known conductors that are reasonably slow, like your antiperovskites, your RF4, SiO4, are all at this bottom left corner of the universe, right? And so these are all the known materials. There are a lot of dots here in the space in between them, and we think that there are potentially a lot of interesting materials out there. It's not just, of course, about ionic conductivity. We are still going through all this to basically figure out which ones we want to attempt to synthesize, okay? All right, to conclude, I just want to say that machine learning actually provides an automatable approach for us to bridge that length and time scale between your first principle methods and empirical potential. Now, the key word here is that they do it in an automatable way. In other words, this is no longer the old days where fitting one EM potential would take the whole PhD, and you basically can use it for one system. We can do a ML potential for any system with higher accuracy within a matter of weeks or months. We can do accurate simulations at longer time scales, and this can provide new insights into solid electrolyte behavior. I didn't talk about the importance of the DFT training data. This will probably be more interesting to people who actually do DFT. What I'm very excited about is this new universal interatomic potential, which I think has the potential for much larger, for large-scale material screening. It's obviously not going to be as accurate as customized potential for one system, but what it makes up for in terms of lower accuracy is universality, okay, right? That you can actually apply it across the entire periodic table like you would do with DFT calculations, okay? And with that, I thank you, and I'm happy to take questions.